Okay, no, you good? You like it? So, it's a great pleasure to have Dr. Irene Fonseca today. She will talk about the homogenization result in the gradient theory of phase transition. Thank you, Diana, and thank you for having me here. And I also want to acknowledge the support of the Kirk Fellowship. I had to make it a little bit short, but so this is the first talk, and there will be a Kirk public talk when I come back in May. So this one is more of a technical talk. Okay, so this is work that spans many years, actually decades even, although of course I'm going to concentrate on what happened, say, the last year or so. And it's also with different collaborators, different trainees, and I'll try to give credit as I go along. So let me start from the beginning. Probably this is something that I should not have to go through with this audience, but let me just briefly refresh your memory that we are going to work with a variational formulation for phase transitions between two fluids. U stands for the density of the fluid, and so this would be the total energy. W is the energy density, has two L's, so you have stability here at, say, -1 and 1, that's where W is equal to 0. This is just the energy barrier that's been on the region, and eventually to minimize the energy, U likes to be either 0 or 1. Now, the way that we force U to not be all the time 0 or not to be all the time 1 is that you have a volume fraction here. So you ask that the average of U is, well, in this case, integral of U is some constant M. So if you divide this by the measure of omega, M should be some number, some value between -1 and 1, so that you force a mixture of the two. So there will be regions where you are 0, there will be regions where you are 1, and M stands for the total mass of the fluid. Okay, so here actually, in general, doesn't matter if it's -1, 1, take it to be A or B. But it could actually be vector values. So these things could be, you could have values in RD if you have a mixture of D fluids. So, okay, so for simplicity, assume that the measure of omega is 1. You take a value of the mass which is strictly between A and B, and so any U that looks like a characteristic function like so, so say A on the set E, B on the complement, provided that the measure of V is the right one, so that when you average out you get M, it will do. So you have a huge non-uniqueness of solutions, anything like that will minimize, will give energy 0. And so you go back to, as was proposed by Gerten, Kahn, and others, and what you say is that, well, okay, so one way of isolating special or privileged solutions is by penalizing the surface energy, which basically stands for this term, right? So if you have a transition layer, say, of order epsilon between zeros and ones, the gradient looks like 1 over epsilon, so this is a term of order 1. And of course, the more transitions you have, the more energy you pay. So here in this case, U is not allowed to be just piecewise constant. It should have a bona fide gradient, so take it to be smooth, C1, C infinity, whatever. But it has to go very fast from one phase to the other, so that this is not going to be too much of energy that you pay there. Okay, so then Mort Gerten conjectured that if you look, by the way, if you just leave the energies like this, you won't see much, because as epsilon goes to 0, this is going to converge to 0, so you don't see anything. So if you think in terms of, say, Taylor expansion, the next term you should divide by epsilon, that's what you do. So you divide your energies by 1 over epsilon, or that's something of order 1, so you see something in the limit, which I will call I0, and this should be I0, not an F. I'm sorry, there's a misprint there. And Girton conjectured that that the asymptotic or effective limit of this sequence of energies should be this one, which up to a certain constant, which is explicitly given by this number here, should be the perimeter in omega, inside of your container of omega, of the region where u is equal to I. That's of course the same as the perimeter where u is equal to v, because you have the two regions, it's either A or B. And you just look at what happens inside. You don't count the part of the boundary of omega, so you don't count the container, you only count what's inside the container. So you go from A to B, you look at that interface, and the perimeter of that is the value of this. Here U stands for, this stands for bounded variation, so it's a function which is very nice, but it can have jumps, and basically its derivative in the sense of distributions is a random measure. Okay, so I'm just repeating what I said. So that was Girton conjecture that actually, if you now go back to your original problem, actually these U epsilons, if you take a minimizing sequence now for this, it won't go to just any characteristic function, basically with values A and B, but it will go to a minimizer now of that perimeter. Okay, to converge to actually a particular, remember I'm using this notation, UCB stands for basically the characteristic function modulo A and B on E and on the complement of E. So now the selection criteria is that these now will not converge to just an arbitrary such function, but one where the support, say where U is equal to A, minimizes the perimeter among all other possible configurations which satisfy the same volume constraint, okay? Because it was fixed from the beginning. In terms of minimizers, minimizing I epsilon or minimizing the viscosity is exactly the same. They have the same minimizers. And this one, of course, as I just said before, has the good taste of being of order 1, so you can see something in the limit by scaling. And that's what we're going to do. Okay, so so that is this is pretty old and pretty much now standard. There's a theorem, first Modica, then it was Modica-Mortola, then Stanford, several versions. This was for the case where you would take values in the reals. When you go to the vector value case, it was work with myself and Tartar, basically around the same time. And indeed, we validated that conjecture of Girton in that we proved rigorously using gamma convergence tools that indeed F epsilon converges to F0. And basically the gamma convergence is just a mathematical way of saying that the basically the lower bound for these energies is F0 and it cannot be any better. That's a tight result. So if you relax, basically you get F0. So there it is. It's that constant, it's explicit and anticipated. And by the way you realize this is actually it's by using 1D profiles, basically hyperbolic tangents that connect A to B across the interface, but they're all 1D profiles at this level. And if any time that you have an integral like this, if here you don't put grad u squared, but if you put an isotropic function of grad u, you still get 1D profiles. The fact that W is double L has no influence in that, except that it will change the surface energy density, which is this level. Okay, so then you can think, okay, so now there are multiple variants of these. Okay, so in the literature you can have grad u to the P, you can have an F of grad u that's highly nonlinear, you can have all kinds of things. You can even have coupled systems which do not necessarily decouple you from grad u, but they couple them, like work of Bushiti and others. Okay, so basically it appeared last year in transactions, work with Jenny Damasu and also with my colleague Giovanni Leoni. And what we've done there was to explore what happens, because until now, well, there will be an exception, and I'll talk about that. The regularizing terms, which are these terms that account for the surface energy, were all local terms in that they could be written as an integral of something. And so we decided to now investigate what happens if you now put a non-local term, and I'll tell you why we thought about that. So that's the typical thing where you have a kernel, and you have then a grad u of x minus grad u of y. So if it was divided by x minus y to some power, you would have automatically some kind of Sobolev norm.
So it's not local in grad u or
in grad u. So this smells like a second order derivative, okay? That's exactly the crux of the problem. So it's this is a technical hypothesis. Basically, without this hypothesis, you cannot do much. But this is just a growth. It just tells you how this kernel behaves. Say at 0 then infinity, but it's harmless. Okay, so for example, if you take this kernel that satisfies our hypothesis, you actually recover fractional Sobolev norms of higher order. Now, so Albert and Bellettini in 1998 did exactly the same, but now with U. So that there was a U and not grad U. And that changes your life dramatically. It's a different ballgame, completely. I mean, there's basically nothing you can recover. At least we could not, from what they've done. And again, the reason, well, and of course the scaling is different, right? Because if you have U, the right scaling is 1 over epsilon, right? While here, if you have a grad square, then you have to have the epsilon because you pick up 1 over epsilon square from the bottom, right? So, okay, but again, the tools have to be, at least our tools were very different. And one thing that took us forever to understand, well, of course, you know you're going to get, again, a 1D problem, a perimeter problem, kind of. And you suspect that while before the surface energy density was very simple, it was a square root of W something, which is you compute by hand with this hyperbolic tangents, 1D. Here you would suspect you're going to get a more complicated cell formula, and that took us maybe, I forgot, maybe 6 years to get there. And you're going to see it's not intuitive. So we played with all kinds of things, and eventually we got there. Okay, this notation is horrible, but I'm going to guide you through that. It's not that horrible. Take a normal cell, a unit vector, right? Nu is a unit vector on the sphere in Rn. You complement that to form an orthonormal basis. And Q nu is just the cube centered at 0 with normals oriented with this, according to this orthonormal basis. So 2 of the faces are orthonormal to nu, and then the other ones are to this, to nu1 to nu n minus 1. And V nu to me is just the layer, the infinite layer that has, again, that with respect to, well, it's actually infinite layer on the new direction. So with respect to the I going from 1 to n minus 1, it's confined between minus 1 and 1, but it's free on the new direction. And this space is just those functions which are periodic in the directions nu1 to nu n minus 1. And x nu is the same as that, except that I want to go from minus 1 to 1, or A to B. So I want to go from, so I have this layer, and I'm going to consider functions which are periodic. So in other words, the only direction that really counts is this one, which is the direction, the normal to your interface. The other ones should not play any role, so you have periodicity with respect to the other ones. But you want to go from A to B. So you're going to find the best way to do it. Okay, and this is the cell formula. So it's, to us, it's not intuitive. So at the end of the day, you get, yes, a gamma limit, which looks like integral over the jump of u, so that's the interface where u jumps from a to b or -1 to 1. But now it's anisotropic. You have a function that depends on the normal. So it's no longer just a constant times the perimeter. That would be the case if psi was constant. It would be like the modica mortula. Now it actually depends on the direction of the normal. And the way you compute this psi is, it's written here. I don't expect you to remember, but it's not intuitive, because you see what we are doing here is that you're kind of localizing the bulk, the W with the cube, that nice cube oriented with a 0, etc. And here, it's absolutely non-locally non-variable, and the other one is integrated over the huge layer. And this is not arbitrary. So if you try to put VV false, it takes you 2 years to realize it's not right. If you try to put VQ wrong, it has to be in this way. So this is absolutely non-intuitive, at least to us. So again, it took us many years to find out that the way that this was here, which again, but anyway, it works. Okay, so another question here that was kind of crucial was that we needed to have an interpolation inequality, because you see, here is how your energy looks like. It's this plus this, and what we know how to do is so the techniques of modica mortula, or then I had worked with Mategatsova, where instead of having here penalization of the gradient, we had a penalization of the Haitian. But somehow we need to be able to have compactness. And to have compactness, you need to bound from below by a function that we know how to work with. And this is highly non-local. So I'd like to be able to say that this is bigger than a gradient or something like that, so that I would go back to modica mortula and be able to do compactness there. So that means you need an interpolation result, and there it is. So I can bound the Dirichlet integral exactly by these non-local functionals. The price to pay is that if I want to bound on an A, this is a neighborhood of A, so that's something a little bit bigger than A. You go up to some distance, and that's the distance. Epsilon is the same epsilon there. This gamma j is a particular parameter that enters in the problem. But this is basically the crux of the problem, is that every time that you mess up, you can control the errors you make in terms of the Dirichlet integral, because you have these estimate from above. Okay, that's just to tell you what this constant is, but I don't want you to worry. And then in the end, what you need to do, once you have that, to compare with the cell formula, you see these are functions which you infimize over functions which are periodic in all directions and go from A to B, or -1 to 1. And so basically you take all your approximating sequences, you have to force them to look periodic in these directions and to look like they go from -1 to 1. That's what we call the modification lemma. And the modification lemma, it's really very painful. It's about 11 pages long to just do this gluing. Takes a long time, and you use the fact that you have always this way of controlling in terms of the Dirichlet integral. Okay, now I want to move to what's next. What's next? Well, let's consider now the case where not only I have these two fluids that I want to coexist with minimal energy, but on top of that, each one of them has some kind of a microstructure. So that now the energy W actually depends on position, and say in terms of, if you want to have a prototype in mind, imagine that W is a characteristic function of some set E times the bulk energy, the energy density of some fluid 1, and outside, or actually this should be omega. Omega outside E, it looks like W2, okay? And then, so you can think that you have, let's say you have a cube. In the cube you have the set E where you put W1, outside E you put W2, and then you expand this periodically, right? So you have this, you have periodic copies of this cube all over, and so you now can talk about X over something which is very small, so that this is going to be a huge, you're going to be all over the place, all over the space, but you do that because you assume that you extend this periodically. Okay, and so there you are. So with respect to the unit cube, we have cube periodicity, then extend this periodically to the whole space. And you're going to have epsilon and delta epsilon go to 0, and then you're going to say, okay, so what's going to happen here? Because now I have two effects, which is that in each one of the two materials I'm homogenizing, right? And then I want to find the best way so that they coexist. Again, I fixed the total volume or the total mass, and so you need to have combinations of the two.
So are W1 and W2 multi-well energies or single well energies?
Okay,
Yeah.
so spoiler alert. So W1 and W2, in what I'm going to talk about, they are double well energies,
Okay.
but they have the same wells.
Okay.
Ultimately what we want to do is to actually consider the case where W of XU has wells at A of X and B of X.
Mm-hmm.
And these are not necessarily the same, even depending on position. You could actually, each one of them could depend where you are, where is your stable state, depending on position. We are not there yet. You're going to see in the end when I have like open problems and future work, that's one of the things you want to do is exactly when the wells are not the same. But here, take W1 and W2, it's here, same wells.
Mm-hmm.
Okay?
Okay. Yeah.
A and B,
Okay.
right? Okay. Now, of course, I should say that as far as we know, this is the work that's been done before. Ancini, Brides, Piatti, 2003. Their problem, W is homogeneous, and what they do is that they consider the homogenization here. In that case, really there is no interaction between the double wells and that. So it's basically an homogenization here. And then Brides and Zepieri, more recently, 2009, has a similar flavor, except that they take the second order derivative. These are piecewise affine functions, which are very specific, and it's a 1D problem. Okay. So, and now, of course, you have three regimes, right? Either delta epsilon goes like epsilon, or delta epsilon goes faster than epsilon, or delta epsilon goes slower than epsilon, right? So the first one that we studied was the case where delta epsilon and epsilon go at the same speed, basically. And then, again, you're going to get what you expect. You're going to get a function which only takes two values, a and b, so it's going to be a characteristic function, up to multiplied by a and b. You get an anisotropic energy. And again, it's interesting here because, as I told you in the beginning, normally when the regularization term is isotropic, you expect to see just a constant times the perimeter, just a complete isotropic surface energy density. Not anymore. Because of the homogenization, you're going to see there's an interaction between the direction of the normal to the interface and the orthonormal directions with respect to each W is periodic, and they may not be the same. And so in that case, you're going to see something that looks like that. So what I'm doing here, again, for a normal nu, you take this Q nu that has two faces orthogonal to nu. You take bigger and bigger copies of that. You average out basically with surface energy, right, to the order n-1. You minimize over all those functions, which again, as I said, are periodic in those directions, go from A to B in the top, from the bottom to the top of your cube. And then you let these cells get larger and larger, okay? That's what it is. Actually, An alternative way of describing this, it could be that you just take the piecewise function, which is a and b, modify it with usual modifier, and if you prescribe that u on the boundaries of these cubes is like the modification, it's the same. It's the same energy. And sometimes it's just easier because it's easier when you're going to do tiling of these things, it's easier to put a modifier with a modifier. So then you have a smooth transition. But that's the same thing. The compactness is not a big deal because you can bound W below by something which does not depend on X, and then you apply the compactness that we know for the classical molecular model, right? Compactness meaning that energy bounded sequences converge up to subsequence to a function which only takes two values A and B and on a set of finite perimeters, so rectifiable. Provided that you have at least linear growth at the infinity. For the gamma limitive, okay, that's not a big deal. Again, you're going to see how to do that. The gamma limit soup is where we are going to have to work more extensively. The techniques that we use here are nowadays are pretty standard for this kind of problems. You know that your gamma limit likes to look like a surface energy, and so you're just going to have to use functional analysis tools like random encoding derivatives and stuff to identify what is the density with respect to that surface energy. Okay, so again, for compactness, I'm just repeating what I said. You go from below. So if you have a sequence of energies which are bounded, you can go below with a certain function W tilde. So you reduce from below to something which looks like this. This is now very innocuous, or 1 over epsilon. If you wish, you can divide through by epsilon. In the vector variant case, you use what we've done, and that's not hard. And for the gamma limitive, again, I'm not going to go into that because that's not where the crux of the problem is. The crux of the problem is on the recovery sequences. So let's see what we want to do. So to prove that it's a gamma limit, I have to prove that that every time that I have a function u, which takes values a on a set E of finite perimeter, takes the value b on the complement, then I can find a sequence of very smooth functions that I plug into my original function, which is this, and these energies will converge to this value, right? That's the crux of it. So it's really tight in that not only this is a lower bound, you can never go below this, but there is one sequence of an approximating sequence of u, so u epsilon converging to u, in some sense, L1 norm, but so that the energies really attain this value. That's what we call a recovery sequence. Okay, so there you are, right? So that's your u. A0 is the phase where u is equal to a. You take a sequence epsilon n going to 0, and you want to find this un, which is which one? So Sobolev, continuous basically, and with gradients in L2 that converge to L1, and such that the limit does not exceed this. Actually, it has to be equal, because if we prove the gamma limitive, they will never go below that number. So it's actually equality here. So what you do first is, this is standard, you localize. So instead of working in omega, I can go back here and say, well, I can also consider these energies on open sets of omega, right? So then I have functions that depend on u and on the domain. So that's a localization, and then up to a subsequence. So if I take this number here, I can look at this as a measure, right? So the measure on a Borel set, or an open set if you wish, is exactly how I compute this energy. and it's enough to do it on open sets, and then there are theorems that tell you that if you define a lambda on open sets in a nice way with certain properties, then you can prove it's a trace of actually a random measure. So you can consider B to be open sets. Okay, and then so the limit of this would be a certain measure lambda. You prove that lambda does not see more than the surface energy restricted to the phase where U is equal to A. Okay, this is a funny symbol. It's basically the boundary, the topological boundary up to a set of Hn minus a measure 0, but it's just the boundary. Okay, and so you will be done, if that's true, and you prove that that's true, you will be done if you prove that the density of this measure with respect to that measure does not exceed that sigma, right? So that's what you want to do. That's the program, right? So if I prove that if I differentiate the measure lambda with respect to the surface measure, the Hausdorff measure, I don't get anything that exceeds sigma on U of x0, which was the density I had before, then I'm done. How do you do that? Well, you do this by using the definition of the Radon-Nikodym derivative. So it's a limit of lambda on a cube, again, oriented with that normal nu of x0. I'm dropping now x0 here. A cube centered x0, radius epsilon, and I divide by this measure on the cube, which is going to look like epsilon to the n minus 1, right? It's a surface measure. In turn, lambda is a limit of this. So for every epsilon, so epsilon is fixed here, but lambda of this object, by definition, is dislimiting, right? That's how I define 4 sequences that converge to U in that cube. The point is, how do we construct these approximating sequences? And the easy case is, suppose that the measure nu is actually, it's like En, right? And which is good, because if nu is equal to, well, one of the orthonormal vectors, suppose it's En, then you complement with the other ones. And now we know that by hypothesis, the W is periodic here with respect to this cube, right? The cube which has this normal. It was unit cube, right? Okay, so what you do is, by definition, sigma on this normal is given by a certain limit that looks like this. All you have to do is, now you're going to have infinite copies of a cell problem here. So I'm going to rescale these U's in this way. And they match well, because remember that the UKs are supposed to go from U0 to U0 across the layer. Okay, you don't have to worry too much on how this scaling works, but the bottom line is that you go back to your energies here, you write it down. Okay, there's a lot of change of variables, but the bottom line is here, is that when you get here, W and that function V, which is the U's which are periodic, they are both periodic with respect to the first n minus 1 directions, which are appearing here. That's a very fast variable, here, here, and there. Epsilon goes first, so this is very fast, right? But that's good, because they're all periodic with respect to those, to Q prime. So the Riemann-Lebesgue lemma says that you just homogenize there. Epsilon disappears. And then when you are here, you go back, change back your change of variables, and that use your sigma. So you prove that this limit of the energies goes back and looks exactly like your original sigma, and you're done. But it could be that W is still periodic with respect to the orthonormal basis, because that's your hypothesis. But now it could be that your interface wants to look like this, where this is A, this is B, or minus 1 and 1, whatever you want to call it. So you want to pass from here to there, and somehow you need to tile these with copies of something that W always counts the same way, so that in the end you just have the right multiple, right? So what you do in this case? So this took us from about, well, we were not working on this full time, I should say, but at this point, this was 2004, 2005, and we just finished it this year. So, so it was basically 2018. So it was 14 years, but not consistently. So, okay. So, the key observation is this, is that actually W has a lot of periodicity, not just in those directions, but in many other directions. And the point is that you can actually look at your lattice and twist it in such a way that you have copies of itself which are rotated and scaled. So the idea here is the following, is that you're going to consider normals which just live in of normals which have rational entries. That's a good thing because it's a dense set, right? So if I can do for this, then you need an approximating theorem that says that if I have a nice profile, a nice set, a finite perimeter, I can approximate its boundary in a strong way by, at least locally, with normals that look like that. I think everybody buys that, right? But that's not enough. The problem is that so picking a normal to the interface that lives there, I think it's pretty acceptable. But then the point is that we actually have to complement these normals with other normals which also live in the same set. So that requires a little bit of linear algebra. And then, so once you have that, so if you then can have a cube which has this normal that lives here, and so that the other n minus 1 normals also live here, you just have to find a huge common denominator, right, that lives in the natural numbers, so that by multiplying them all, you go back to all integers. You see what I'm saying? So that is the point. So, okay, so actually there's a very old theorem that goes back to 1837 that tells us how to do this. And so by using this theorem, what we could prove was that, okay, so I pick a direction that's good for my interface, but now I move it just a little bit so that it now has integer entries, but I can now complement it with n minus 1 that all live in the same set. Lambda is that set. They all live there, and then I find a very large multiple, lambda, so that now I have periodicity with respect to each one of these, provided I multiply them by this, right? Because if I multiply by very, very large, I cube the bottoms, I cube the denominators on all these normals we like. So that is the key thing that finally made it this work. And there's another result that also we need, which is that so when you start messing this up, which is you have a rotation, and so you have a normal nu, and then you want to make it to look like a EN, so you have a certain rotation S, and then the point is that you can find another rotation that now maps all the remaining vectors of the orthonormal basis, the canonical orthonormal basis, maps it into that set, and you stay very close. So that's true for every epsilon. So you can control the error that you make. This is all linear algebra. Okay, so that's I'm just reminding you how sigma looks like, right? That's the cell problem. These are just unit cubes, so at the origin with two-face orthogonal to nu. And Well, first you have to prove it. This is well defined and finite, but that's okay. That does not depend on the choice of modifier. That's also fine. You prove it is upper semi-continuous. And you also prove that actually it's enough to consider cubes that have these faces that belong to that set. Okay, and so there you are. So you take a normal nu that lives there. So now, okay, you want to have your periodicity. It's with respect to the orthonormal base, but your normal to your interface goes like this, right? You're going from A to B, right? So it goes like that. But basically, you now do the same kind of tiling, essentially by following what I said. So you take a point on the interface, you take the normal, you find a rotation and a lambda, so that you have this now periodicity with respect to a very large lambda nu. And then once you have that, you just write sigma with respect to these very large cubes that are chosen this way, and the rest of the proof, okay, you work a little harder, but the main idea was here. Okay, and then how do you wrap up? Okay, that's now it's not particularly hard. Given an arbitrary U, you can always find a sequence of polyhedral sets which approximate your set of finite perimeter in a strong way, so perimeters converge to perimeter. Because this set is dense in the sphere, you can require that all these normal to these polyhedrals live in there, because you prove that your surface energy is upper semi-continuous. There's a theorem due to Reshetniak that tells you that surface energies behave nicely in terms of lower semi-continuity this way. Actually, it was enough to have lower semi-continuity, but it works with soup. That's fine. And for each one of them, because now these are good, now these are polyhedral sets with normals that we can now control as before. For each one of them, you now know that you can find the recovery sequence, and then you just analyze. So that's basically the way you do. Now, other scaling limits. Well, let's not consider the case where, so the one I talked about was basically when epsilon and delta epsilon was commensurate. They were basically at the same speed set. But now suppose that this goes much faster than epsilon. So delta epsilon over epsilon goes to 0, right? So what do you expect? You expect that if this goes faster like an epsilon square, that first you're going to homogenize, and then you have a phase transition, right? So you expect that you're going to replace this by something that has no longer this fast variable, which is the homogenized energy, right? It's just average out with respect to the fast variable. And if that's true, then once you're here, you're done. That's Monica-Martel again. That's classic, right? So the question is, how do you go from here to there? So normally you should have epsilon over delta epsilon. You need a little better. You need epsilon to the 3/2. It's technical, and I'm going to show you where. The work of Andrea Brides also had this epsilon to the 3/2. And I'll show you where it comes about. So I don't know if this is necessary. I don't know. It's certainly sufficient, but I also don't have counterexamples. We didn't work that much.
It's not really optimal.
I have no idea.
Okay.
But I'll show you where it enters, and I think it's not, at least where it enters for us, I don't think it's optimal. It's a one-line proof. It's a Poincaré kind of thing. So it's kind of a funny thing because, well, I'll come back to that. Okay, so if it goes like that, then yes, then it's isotropic. It's a perimeter times a constant. This is just homogenized energy, and the constant is the same you have for Monica-Martel, except now with the homogenized energy, right? So again, it's 1 d geodesics going from A to B. You minimize over like so, you get a constant, and you plug it in there, and that times the perimeter. Okay. So the point is, so the outline is, okay, you compare the bulk energy we had with the what I call WH, you're going to see that that's where you need this control of the delta versus the epsilon. Once you hit there, you, in the vectorial case, use the work with tartar and you're done. So basically that work that I keep referring to, in a nutshell, just says that functions of this form, vectorial or not, always have a limit that looks like a constant times perimeter. That's what that result says. Okay, so the key tool is how can I compare my original energy that has this business here with this one, right? How can I compare? This is the same, so keep it there, it's not going anywhere. What I want to say is that the difference between this and this goes to 0, then I'm done, right? So what is the theorem that you need to prove? That if you have a sequence of epsilon n and delta n such that this is bounded, because that comes from your energy, right? This is bounded, right? And if this goes to 0, that's the problem. Then indeed you can compare, and this is 0, so you can replace in the energy, you can replace this one by that, and then you're good. No more homogenization. Well, the homogenization is there, but then you have like modicum ortho. Okay, so if you had a p, for example, you would need a 1 plus 1 over p, but you're going to see exactly why that's going to work. Here, it's p was equal to 2, so that you had a 3 halves. Same as, again, a sine-Bradis Piat. I don't know if you need it or not, but basically this is, let's see, I'll show you where, I'll show you how it goes. You had the scale delta epsilon, right, which is the scale of homogenization, so you just take your omega and basically write it as cubes, as a unit of cubes. Right? This is just a grid size delta epsilon. You have a little remainder. The remainder is controllable. It's controllable by delta n, right? It's just what you left at the boundaries. So don't worry about what happens there because it goes to 0, because it looks exactly like delta n of epsilon n. So this is good. Here, just having this going to 0 would be enough. Okay? So let's just now look at what happens in all these copies of these cubes of size delta epsilon. And so it's enough to control now this difference, right? On these cubes. You do change of variables. There's nothing magic there. This one does not have a z, so writing these or writing this is the same, because when I integrate in z, I get delta h, right? WH, right? So this and this is exactly the same. I just put another integral in there with a phantom variable. Okay, now I do Fubini's. So
I mean, it's not a phantom variable. It's the self formula for WH.
this is the WH is exactly this integral with respect to z.
Yeah. Yes.
Right? So for y fixed, that's what it is. So this is just writing WH, right? So I put an extra variable z. This does not have z's. So that's exactly what I wrote there, okay? Except that I can do Fubini's, okay? And I do Fubini's there. Now z is there. I do Fubini's. So now, y is the same y. So if these two are comparable, assuming Lipschitz properties, whatever, and so if I can control this, I should be able to control that, right? If this is Lipschitz. Okay, so now let's look at that. So Poincaré, you pick up an extra delta n, right? From there. And then of course you change back variables, so you get delta n over epsilon n. This here reduces just to integral basically of omega. And then you're stuck. Because we had a control on this. This was a control we had. So how do you go from here to there? I have to produce an epsilon n to the 1/2, so I have to multiply epsilon n to -1/2. So it's okay, maybe there's a better way of doing it, but this is exactly why we need it. It's the only place where we need it, is right here. It's to control this error, because I only have bounds. Your energy only has bounds there. It's the integral of epsilon grad u squared. That's the bounds. But the Dirichlet is multiplied by epsilon.
So essentially, you're saying that it's not clear if you will be able to control perimeter, and that's why you have to do this trick.
Yes, yes. But I think, so in our case, I think this is probably not optimal because I mean, this is really brute force here. I mean, it's forcing it to look like epsilon n and it doesn't want to look like epsilon n. Okay, so, okay, but then, okay, the rest is fine. Okay, so there is then a question, okay, then at some point you need to use the fact that, to use these Lipschitz, that WH actually looks one-dimensional. So, okay, but that's a different story. And you can use some uniform boundness on there. So let me just wrap up here and say, okay, when epsilon is less than delta epsilon, I wrote forthcoming, but that's really wishful thinking because we have no clue how to do it. So epsilon less than delta epsilon means what? So you go back here. This is something that also I've been chatting with Adriana, and also Riccardo Cristoferi and Adrian. We are all stuck there. Where's my thing? I'm going too far out. Okay, sorry. Here. So the case now is suppose that delta epsilon goes slower than epsilon. So morally, this looks like first you have the phase transition, you go to a surface energy, right? Because first you should have a kind of Hilliard kind of thing, and then an homogenization. So you're going to have an homogenization on a manifold, right? Plus things don't look well because then on the manifold you have your U's are not going to be well defined. So we have no idea how to do this. So, but that's basically what would require. I should actually mention there's a very recent, well, actually 2 papers by, let's see if I give them justice, Cagnetti, Dalmaso, Scardia, and Zepieri. One I think is of last year that appeared, which is deterministic, and one is in the archive, this archive, not Arman, the archive out of Cornell. Where they do actually stochastic homogenization, which is actually something that eventually I would like to be able to do, is to do non-local stochastic homogenization here. And also in the case where the wells are moving, but what they do is they take, also using stochastic homogenization, they already start in SBV or BV. So they basically are already working with surface plus bulk, and then homogenize the two. So it's a different problem because what we don't know how to do is to go from our Carnegie-Hilliard, which is the competition between the two terms, to a surface energy, which hopefully still has some homogenization to do there, and then homogenize. And we don't know how to do this. Okay, but then, that's again, eventually we are doing this because we'd like to go to the case where you have actually gradu, where in the nonlinear elasticity you should have some kind of a growth like this. And now this was actually done, with the non-physical growth, which was strained to the P. This was done also with Conte and Leoni quite a while ago. With the usual rigidity kind of growth, it was done by, and this is not homogenization, this is just Carnegie-Hilliard. Because you first need to know the Carnegie-Hilliard to then put homogenization on the Carnegie-Hilliard, otherwise you cannot start. So even without homogenization, so with this one, basically here, or nothing here, just double grad U, on the plane by Conte Schweitzer in 2006, and in 2010 by Elisa Davol and Manuel Friedrich, but they had to add kind of a curvature term to the functional. And it's not trivial. Okay, so that's basically where we are. So we only solved 2 regimes. This one, which was actually what we have liked to do from in the beginning, we still don't know how to do it. It's very complicated. And then, of course, there's all kinds of things you can do there. Okay, that's a good place to stop. Thank you.
Thank you very much. Other questions, comments?
So do you have an immediate example where I could think of applying? Let's see.
The
what
cases
kind
that I think of,
system?
the case that I think of again is like, as I said, a characteristic function times one material plus another one on the complement. And then you have a tiling of that periodically. And that's what you're going to, except that it should be with grad U and not with U. Right? So, but you start with U and with them some. But that's what we have in mind. What we have in mind is actually mixtures of two materials.
That's right, mixtures.
Yeah, it's mix of two materials. It's like, it's exactly the prototype. It's a characteristic function. So imagine that you have on a cube, and I give you, like, you have a matrix of, say, material A, you put inclusions of material B, and now you're going to tile the whole space like that, but then you're going to have copies and copies which are smaller and smaller, right? So in the end, you're going to have a microstructure, right? So you're going to look an homogeneous kind of thing, right, if you look from far.
So it's a mixture of two-phase materials.
It's a mixture of two-phase materials. That's what this is. Okay, that being said, eventually, you know, if you have a PT who's very brave, you can get him or her to do N materials, right? But you start with two, right? You start with two. But even there, you see, because it's the thing that that confuses for many years, actually I would say 14 years, was exactly how do you conciliate how the materials want to homogenize with this periodic tiling, but at the same way, how do the phases want to come together between like the global A and the global B, and the normals may not be aligned. And that's what we were stuck for years, because we didn't know how to do this. So.
Now, could you have something that instead of tiles is just layers? Because I could think of more applications, like instead of tiling, just to cap periodicities in one. In four
Yeah, but
dimensions.
that's a particular case of this. I mean, when I think about the tiling, it's just an example, right? But you could take a W that looks exactly like a laminate,
Right. Yeah.
right? With that periodicity, you just laminate in some way with a certain volume fraction delta epsilon, right? So you could do that, yeah.
So may I ask you more so about this scaling epsilon to the
3/2.
So do you have a 1D computation that somehow justify this? So I guess in 1D with some special.
Yeah, but so
in 1D there are
Okay,
not much
so, yeah,
possibility for homogenization.
Right. So the 1D computation, if we just want to do it as we were doing, which is to force to look like epsilon u prime squared, you get the same. So there's no.
No.
It's
Of
not
course,
really
of
gonna-
course,
yeah.
of course. I was saying that in 1D, I guess you would be able to essentially
Yeah.
compute the interface. I would say, no, you have a material which is half and half, so you exactly know the microstructure, and you assume having a one interface, and you try to see what. So instead of approximating the oscillating potential
Right.
with the homogenized one, you should have some.
Yeah, no, you do it by hand.
Yeah,
I mean,
it's,
the scale is
yeah.
there. So,
Yeah. So I
no,
wonder if you really need this.
I don't know if Ricardo or Adrian, so my student, well, my postdoc, my student, or former, did the 1D. I didn't do. So actually, that's an interesting question. Maybe it's a simple computation. I don't know. Maybe we'll be surprised. I don't know. Definitely in more than 1D, if you just want to do it brute force, but I think again it's pretty crude what we try to do. So there may be more, I don't know, or better interpolation results, maybe even like okay, because we just go brute force Poincaré, right? So maybe that better interpolation results than.
But it kind of looks like you need control over perimeter. As long as you
Yeah.
control perimeter, you're done. And it's kind of highly unlikely that you're not going to control it because I mean it's.
Well, yeah.
I mean
I agree. I agree.
I mean, in this computation, when you use the Poincaré, you never use the double well potential, which is used.
No,
in the,
exactly.
in the
well,
chemical,
that's
so-
that's why it's very true. That's why it's very crude, because we just look at the epsilon times grad u squared, right? And we ignore everything about that there's something else that's telling you something, right? And we do not use it. So, yeah, again, I mean, it's a gut feeling, but my gut feeling is that epsilon to the 3/2 is maybe artificial, So, but again, I may be surprised. Maybe something horrible happens,
Fractals?
I don't know, below that, I don't know. So, I don't know. But it's, that's where we are.
Some more questions? So if not, let's thank
Thank you.
again.